Bismillahirrahmanirrahim. I would like to quote an ayah from the Quran Pak. And when your Lord said to the angels, I'm going to place on the earth a vicegerent. So my dear student, you all are born leaders. Today we will solve this question number 1 from our paper. (9701/42 October-November 2020). Question number 1. The rate of reaction H2 plus I2 goes to 2HI is studied. A small amount of H2 is mixed with a large excess of iodine at a temperature of 400 Kelvin and the reaction is monitored. The graph obtained is shown. So you can see relative concentration of hydrogen is plotted against time, and the concentration of iodine is taken in large excess. And the question is, suggest why large excess of iodine is used in this experiment. So whenever we take large excess of one of the reactant, we need to make it constant. And as you know, when we take large excess, change in concentration of that substance is negligible as compared to the large excess present. So we take it because we want to make its concentration constant. So it stays constant. Now the next part of this question. The reaction is first order with respect to hydrogen. So use the data from the graph to confirm this statement. So dear student, whenever you are provided with the graph, you don't have to write it like it is first order as you can see the graph from the graph. No, you need to show your working. You need to calculate how you reach to the conclusion. So you have to solve this question in this manner. First half-life concentration, when you halve the concentration from 8 to 4, you see time 45 seconds minus 0 second, you get the 45 second. This is the first half-life. And the second half-life, when you halve the concentration from 4 to 2, you can see time is 92 second minus 45, you get the 47 second, which shows that your half-life is approximately constant. So that indicates that the reaction is first order. Now the table is provided and you need to find the order of reaction with respect to iodine. So in this question, you are already provided the order of reaction with respect to hydrogen. So you can take any experiment. I have chosen experiment number 1 and 2, and this is the simple way to find experiment 2 divided by experiment number 1. So the concentration of experiment 2 for hydrogen is taken here, and for iodine is taken here, and rate, their respective rate is written against them, and we solve it. We get here 100 and we get 10 raised to the power 1. So we solve it and we get the order of iodine first order. Now the third part of the question, use the information. You need to write the rate equation, and then you need to determine the K, and you need to determine the units. So as you know the order of hydrogen and iodine, you can very easily write the rate equation. See, K, concentration of hydrogen is raised to the power 1 and iodine raised to the power 1, and by simply putting the data, taking the data from the table, you get the K, that is 2 into 10 raised to power minus 13, and units you can calculate by just putting the concentration into concentration and units of rate, you can determine the K. Now the very important part. At 400 Kelvin, the rate constant means K for the forward reaction is approximately 1000 times greater than the rate constant for the backward reaction. So this is the main statement. The overall order of the forward and backward reactions are the same. So this is forward reaction, formation of hydrogen iodide, and breakdown of hydrogen iodide is a backward reaction. Use this information to explain what will happen if equal concentration of hydrogen iodide, hydrogen and iodine are mixed at 400 Kelvin. You should comment on the relative initial rates of the forward and backward reactions and the position of the equilibrium. So if we answer it simply, that forward reaction is faster than backward reaction and reaches equilibrium on the product side. Initially, they have already given us that the rate of forward reaction is already greater than the rate of backward reaction. So they are not same, initial concentrations are not same. Okay, and for answering this question, you need to consider given assumption, that is equilibrium rate constant for forward reaction is approximately 1000 times greater than the rate constant of for the backward reaction. So equilibrium will only be reached when HI is much greater than I2 and H2. Okay. Now at 400, now you can see at 400 Kelvin, the rate constant for forward reaction is much greater as compared to at 700 Kelvin. Your rate constant decreases. So that indicates that your forward reaction is exothermic. So delta H for forward reaction is exothermic, and you determined by just comparing statement number 1 by statement number 2. Statement given above, which is for at 400 Kelvin, and statement given below, which is about at 700 Kelvin. You compared the rate constant and their rate of reactions, and backward reaction is vice versa. Now see, forward reaction is negative and backward reaction is positive. Equilibrium position further left at higher temperature. So you understand, for forward reaction what happened? Equilibrium position will move backward at higher temperature as the forward reaction is exothermic. Now what is the explanation? As we have already discussed, and I have written here, although high temperature increases both the rate, you must understand that you need to mention at high temperature, you have to mention both reactions. At high temperature, as the temperature increases, both rate of forward and backward reaction increases, but in this case it increases the rate of backward reaction more, as it is mentioned here according to the rate constant. So the position of equilibrium move towards H2 and I2. And that's it. Thank you very much. I hope you understood it well. If you have any question, please ask in a comment section. Thank you.